Hi guys, welcome to Daily Problems 1, Calculators Allowed. Alright, so hopefully you guys have the problems in front of you. If not, I was kind enough to put them on the screen. So here we go. Alright, the shaded region R is bounded by the graph of y equals x squared, which is the parabola you see, the curved function, if you guys, hopefully you know what a parabola is, and the line y equals 4, which is the line, as shown in the figure below. Okay? And find the area of R. So here we go, area of R. Now the area is the one where we don't have to do any extra work. There's no pi's, there's no squaring, it's just the simple area. Okay? So here we go. To find the area, we need to decide if we want to integrate in x or in y. They've given us everything in x, so it seems like x is the way to go. And we're going to draw an arrow going from our top function to our bottom function, right? If we're integrating in x, we're going to point our arrow down to the x-axis, right? And we're going to integrate from our top function to our bottom function. So, our top function is 4 minus our bottom function, which is x squared, dx. And then we want to know our bounds, and remember we want bounds in x. So whatever this point is, and whatever this point is, we want the x values. Okay, we can set them equal to each other. X squared equals 4, and take the square root. X equals not 2, but plus or minus 2, right? And that's in x, so that's all we need. Minus 2, positive 2. And calculators are allowed, so we're going to go to our handy calculator. Now I'm going to do these in Classic, not Math Print, because I'm assuming that Math Print people have an easier time remembering how to do this. So we're going to go to Math 9, which is F-N-I-N-T, and then it opens a parenthesis for us. So we don't need to put an extra one. We're just going to use the regular parenthesis here. We're going to go 4 minus x squared. Then we put in a comma. Then we put in an x. We put in another comma. We say negative 2, comma 2. Close parenthesis and hit enter. And we get 10.66666667. Or if we prefer to put it as a fraction, we say math 1 and hit enter, 32 thirds, right? And if we go back, right, 32 thirds. Now we're missing something, right? Sorry, no, this is area, so we're done. Sorry, I'm already thinking about part B. So that's it, 32 thirds. Or if we wrote that as a decimal, we'd write 10.667. Okay? 3 decimal places and no more. Okay? One or the other, you don't write both. Okay. Part B, which I think I've already left space for on the next slide. Okay. Find the volume of the solid generated by revolving R about the x-axis. Okay. So we're finding volume, and we have to decide, do we want to do this in disks or in shells? Now, we've been doing these integrals in x, right? We've been integrating in x. So if we integrate in x and we revolve around x, revolving around x, integrating in x, they match, so we're going to use disks and washers, right? Okay. So if we use disks and washers, we notice that this is going to be a washer problem, right? We have 2 different functions, right? We can almost see it if we revolved it. We'd have one function there and another function here, right? So we have an outer radius and an inner radius. So what does that mean? Well, that means that our outer radius, that's the worst line I've ever drawn. Okay, our outer radius right here is going to be our first problem, and then our inner radius here will be our second problem. Okay, not so bad. So we take the integral, same bounds, right, because we're still integrating in x, so we still want our x bounds, so negative 2 to 2. And then our outer radius, which is 4, and we square it, right? Outer radius squared, minus inner radius squared. And the inner radius would be x squared, and we square it. And dx. And we're missing one last piece, which is pi on the outside. So we always have pi r squared and the thickness. And if it's washers, that radius, outer radius squared minus inner radius squared. Okay? And you don't have to rewrite it, but we notice that this is 4 squared is, of course, 16 minus x squared squared is, of course, x to the 4th. Okay, we don't have to rewrite it, but we want to notice that when we go to put it in our calculators. Okay, and of course, it's a calculator problem, so we don't bother doing this out by hand, right? We just plug it in. So we're going to say math 9 is FNINT, and then we plug in our function, so 16 minus x to the 4th power. So there's our function, comma x, comma, -2, comma 2. And we hit enter. 51.2. Or if we prefer, math, hit enter, 256 fifths. Right? So some kind of funny looking fractions here. Okay. And so that's 256 fifths, and of course pi. Right? So if you put it in to your calculator with the pi out front, then you're not going to be able to get a fraction. If you put it in without the pi, then you can put it in as a fraction and put the pi in afterwards. Okay? Obviously, you do not have to put it in as a fraction. You can put it in as a decimal. The one thing you don't want to do is put in 51.2 pi. They don't want to see a decimal and then pi. That just looks funny. So don't do that. They don't like that. So you either put it in as a decimal or put it in as a fraction times pi. Okay? But don't put it in as a decimal times pi. That just looks funny. Okay? All right. So that's part B. Part C. There exists a number k where k is greater than 4 such that when r is revolved about the line y equals k, and I'm going to stop there for a second. So we see that we have a line y equals k. So I'm going to draw in that line right now so that we have that piece of information dealt with. So y equals k is a line, and k is greater than 4, and we know if it's y equals, that means it's a horizontal line, right? Y-axis is this way, and the tick marks go this way, that means it's a horizontal line. And if k is greater than 4, it's a horizontal line. I don't know exactly where it is. I do know it's somewhere up here, though, right? I know it's not down here somewhere or below the axis. I know it's above 4, so it's up here somewhere. Okay? Okay, so I've dealt with that. And I'm revolving around this line. Okay. And the resulting solid has the same volume as the solid in part B. Okay, so let's grab that. 256 pi over 5. So, whoops. Not what I intended to do here. I intended to get this thing right here. So that we can bring it over from the last problem. So we don't forget, no, not what I wanted. Okay, here we go. So we remember this from the last problem. Okay. Write but do not solve an equation involving an integral expression that can be used to find the value of k. Okay. So we want to find the volume of the solid that results if we revolve r around this line. So let's start with that. Okay? And we'll worry about this other part in a minute. So, okay. So I'm going to take this and I'm going to revolve it around k. Well, that's a slightly different story than when we were revolving around the x-axis, because now we're going to have this situation. So we're still going to have washers, but now our washers are going to be up here instead of down here, right? They're not going to be over here anymore. Okay, something parallel to the x-axis. So if it's parallel to the x-axis, we can still use washers and we can still integrate in x. But now they're up here. What that means is that we're now going to have the outer radius is going to be something more like this, and the inner radius is going to be something more like this, right? So a slightly different situation. All right, not so bad. We can deal with that, right? Okay, so how do we deal with that? Well, pretty simple. We're still going to have the same bound, right? We're still going from here to here, and we're still going to have a pi on the outside, right? So we're still going to go -2 to 2, right? And we're still integrating in x, so we still point to the x-axis. So we're still going to say, well, now, we may need a little more room than that. So I'm still going to say the outer radius minus the inner radius, but now the outer radius goes from k to x squared. So I'm going to say k minus x squared, and then it's still outer radius squared, minus, and then I look at the inner radius. The inner radius says k minus 4. So k minus 4 squared. And then dx. Not so bad, right? And then remember that, oopsie, let's not do that. We're going to take, maybe it won't let me. I don't think it will. Okay. And then all I have to do is say, I'm going to take this, I don't have to solve it. All I have to do is say this is equal to this guy, which is getting lost over here, but so I'll put it down here. Right? The resulting solid, which would be this, has the same volume as the solid in part B. And there's the volume from the solid in part B. So we don't actually have to solve it. We just have to write an equation. And here's our equation. So that's it. Okay? All right. Moving on to question 2. Let v of t be the velocity in feet per second of a skydiver at time t seconds, where t is greater than or equal to 0. After her parachute opens, her velocity satisfies the differential equation this should be a v, sorry about that, dv dt, well, you get the idea, equals negative 2v minus 32 with initial condition v of 0 equals negative 50. Use separation of variables to find an expression for v in terms of t, where t is measured in seconds. Okay, so here we go. dv dt equals negative 2v minus 32. And I remembered that once upon a time someone said that whenever you can, always factor first. So I'm going to factor this into negative 2 v plus 16. Right? Just simplifying the equation a little bit. Okay, now separation of variables, the first step is to separate the variables, right? So I'm going to make this into dv over v plus 16, right? We never take those constants with us, we always leave them behind, equals negative 2 dt. Right? And then I'm going to integrate. Okay? Now this guy here, right, we know how to deal with that. This is u substitution. U equals, that's a terrible u, u equals v plus 16, du equals dv, which then gives us the integral of du over u, better known as the natural log of the absolute value of u, which equals, going back to our original variable, the natural log of the absolute value of v plus 16. Right? And then this guy, negative 2 dt, integrates to negative 2t plus c. Pretty simple on that one, right? So we'll put them back together, negative 2t plus c. And now we got to solve for v, right? We want v by itself. So we're going to say e on both sides, right? We're going to raise both sides to the power of e, and these go away. And then we're going to drop the absolute value because e is always positive, right? So e is always greater than 0. Oh, the pen is running out of ink. Okay, greater than 0. Okay. And so then we're going to get v plus 16 equals e to the negative 2t plus c. And then I can separate this into e to the negative 2t times e to the c. Right? We remember that if I had a to the m times a to the n, that was a to the m plus n, and we can also run that in reverse, right? So we can use that here. Okay? And then we can say that, well, e to the c is just another constant. So we'll write that as c1 e to the negative 2t. Right? But we don't really want v plus 16, we just want v. So I'm going to subtract 16 from both sides, and we're going to say that v of t, right? We didn't write it as v of t, we wrote it as v, but v of t is negative 16 plus c1 e to the negative 2t. Okay? But we're not quite done yet. They also tell us that v of 0 equals negative 50, right? So that's our last step. So I'm going to say v of 0 equals negative 16 plus c1 e to the, well, negative 2 times 0 is 0, and e to the 0 is 1, right? So that's going to be negative 16 plus c1. And v of 0 is negative 50. Right? And I add 16 to both sides. Okay? Be careful when you do this, because if you add 16 here, you add 16 here, you also need to add 16 here and add 16 here. Otherwise, you are violating your equal sign, which is why I didn't do it back here. So be very careful about doing this. At any rate, so now I'm going to have c1 equals negative, I believe that's 34, if I've done that correctly. So our very final answer, v of t equals negative 16 minus 34 e to the minus 2t. All that work for one teeny tiny equation. Seems like too much work, doesn't it? Okay. Now I'm going to take a photograph of that answer because I have a funny feeling we're going to need it not too long from now. Okay. Apparently I didn't write too straight. Okay. Alright, so that's part A. Part B. Terminal velocity is defined, terminal velocity is defined as the limit as t approaches infinity of v of t. Find terminal velocity of the skydiver to the nearest foot per second. Okay. That sounds like a lot of work. It's actually very simple. Terminal velocity is defined as the limit as t approaches infinity of v of t. Stopping right there. All right. The limit as t approaches infinity of v of t. Okay. The limit as t approaches infinity of negative 16 minus 34 e to the negative 2t. Okay? I can plug infinity in there, and, well, e to the negative 2 times infinity, well, 2 times infinity is infinity, so I'm basically getting, for this part, e to the negative infinity. Well, e to the negative infinity is 0, right? I plug in negative infinity as an exponent, and I'm getting smaller and smaller and smaller. Or I can think about the graph, right? That's what's happening as I go to negative infinity, right? Or thought about another way, this is basically 1 over e to the infinity, right? And e to the infinity is huge. 1 over a huge number is 0, right? So if this is going to 0, I essentially have negative 16 minus 34 times 0. 34 times 0 is 0, so I essentially have negative 16 minus 0, or negative 16 feet per second. So they like to try and trip you up with that nearest foot per second thing, but this is actually a very simple calculation you don't need a calculator to do. Okay? All right. Moving on, part C. I have a funny feeling I'm going to need that formula one more time here. It is safe to land when her speed is 20 feet per second. At what time t does she reach this speed? All right, so negative 16 minus 34 e to the negative 2t. So that's her velocity, and it is safe to land when this velocity equals 20 feet per second. Now we have to be careful because this here is velocity, and what they gave us is speed. Notice that velocity, all the velocities so far have been negative. There's a reason for that, and the reason for that is that she's traveling downward. So it'll be safe to land when her speed is 20 feet per second, but her velocity is negative 20 feet per second. So we'll want to make that negative 20. Okay, so that we'll have to be careful about that. Okay, so that's the trick there. All right, so we add 16 to both sides, and we get negative 34 e to the negative 2t equals negative 4. And we'll divide by negative 34. And that goes away, and we get e to the negative 2t equals 4 over 34. Then we take the natural log of both sides. And this is basically not a calculus question at this point. Negative 2t equals the natural log of 4 34ths. And we divide by negative 2. And this is, of course, a calculator question at this point. Thankfully, I have one of those. And we should get the natural log of 4 divided by 34 divided by negative 2. And always remembering that you need 3 decimal points. And you cannot say 1.07. Yes, I know that this is a 0, but saying 1.07 and stopping there implies that it's 1.07 exactly. So you must say 1.070 to show that it's not, that it continues after that. So we want 1.070. And our units here are seconds, right? Okay. And that's it. So the big trick here is noticing that this has to be a negative 20. Okay? And if you don't put in negative 20, you're going to end up with, this would have been positive 20 plus 16. That would have given you 36. You would have ended up with negative time. So obviously that would have been a big problem. Okay? Okay, so moving on to the multiple choice. During a certain epidemic, the number of people that are infected at any time increases at a rate proportional to excuse me. Excuse me. During a certain epidemic, the number of people that are infected at any time increases at a rate proportional to the number of people that are infected at that time. Okay, so just that right there. The number of people that are infected at any time increases at a rate proportional to the number of people infected at that time. That should tell you right there that you are dealing with, hopefully you've guessed it at this point, you are dealing with exponential growth and decay, right? This is, right? This is a rate, right? Increases at a rate. So that's dy dt proportional to equals k, the number of people, y, right? So, does this mean you have to go through the big long derivation? Absolutely not. Do not do the big giant derivation. Why? It's multiple choice. Nobody cares. This is where you go, hey, I don't have to do the big long derivation. I'm just going to go y equals y0 e to the kt. We know that's what exponential growth and decay looks like, and we don't have to go through the big long derivation because it's multiple choice. If 1,000 people are infected when the epidemic is first discovered, hey, 1,000 people are infected when the epidemic is first discovered. Notice first discovered. Hey, that tells us y0, right? Let me do that in a different color here. So, increases at a rate proportional to, that gives us y0 equals, y equals y0 e to the kt. First discovered, right? The 1,000 people are infected when the epidemic is first discovered. That gives us y0, right? y0 is 1,000. Cool. Y equals 1,000 e to the kt. Done. Next. And 12,000 are infected 7 days later. Ooh. Quickly spreading. So, hey, we can do that. 12,000 people, that's y, so 1,200, not 12,000. 1,200 equals 1,000 e to the, still don't know k, but t is 7. Okay, hey, one equation with only one thing we don't know. So we start solving. And here's where you can feel free to be absolutely obnoxious. You don't, no one's going to see the work. So natural log, that goes away, divide by 7, Okay, I'm being a little more obnoxious than, you have to be, but, right? So we want to see that in a little bit of slow motion. Right? So we divide by 1,000. And we get 1.2 equals, e to the 7k, natural log of 1.2 equals 7k, divide by 7. I have no idea what that is, but I'm just going to leave it because who cares? So I now know that y equals 1,000 e to the natural log of 1.2 divided by 7 times t. And then the final step, how many people are infected 12 days after the epidemic is first discovered? So 1,000 e to the natural log of 1.2 divided by 7 times 12. Definitely a calculator situation. Hopefully I'm going to remember all that to plug it into my calculator. So here we go. We're going to have 1,000 times, I'm going to need more buttons here, times e to the natural log of 1.2 times 12 divided by 7, close parenthesis, enter. And there's your answer, 1366.907, and I believe they rounded that to 1367. There's your answer. Alright. So the point is, you can be as messy as you want, you can show as much or as little work as you want. This is multiple choice. No one cares. Okay? Number 4. The area enclosed by the graphs of y equals x squared and y equals 2x plus 3 is. Okay, so here's a hint. Y equals x squared, y equals 2x plus 3, positive slope, kind of like that, right? Alright, here we go. We need to know what that point and that point are, right? We don't need to know exactly what it looks like because, well, it doesn't matter. It's multiple choice. And we set them equal. X squared, 2x plus 3. Move them to the other side. Minus 2x minus 3 equals 0. No one really cares. It's like x minus 3, x plus 1. Right? So that's probably negative 1. And that's probably 3. So we integrate, right? So we're going to take the integral from negative 1 to 3. And then we're going to go from the top function to the bottom function. Now let's say you had some funny graphs and you had no idea which one was the top function and which one was the bottom function. Let's say you're going, I'm not really sure what they look like. Now in this case we know what they look like. But if you're not sure and you're really pressed for time, just put them in absolute value. Because the absolute value will take care of which one is the top and which one's the bottom. And then go x squared minus 2x plus 3. And the absolute value will take care of which one's the top function and which one's the bottom. Dx. Now be careful, because you can get in trouble if they flip over each other a few times. But this will take care of most of your problems on an AP exam. This only works if you're on a calculator section. So beware, if you're on a non-calculator section, obviously you could put them in absolute value, but then you're going to have to go back and figure out where they flip over each other so that, and then un-absolute value it. But if you're on a calculator section, you can do this to save yourself some time. Okay? So, then we put it into our handy-dandy graphing calculators. And we can say math 9. And then if you're not sure where absolute value is, it's, I believe, math and then number. There it is. Absolute value. And then we had x squared minus, and then parenthesis 2x plus 3. And now be careful, we've had a lot of parentheses. So I'm going to close the parenthesis for the 2x plus 3. I'm going to close the parenthesis for the absolute value. Comma, x, comma. We went from -1 to 3, and then I'm going to close the parenthesis for the FNINT. Okay, and hit enter. And oddly enough, I recognize this somehow. This seems like we've seen this before as 30 from a previous problem. But if we don't remember, go to Math 1, hit enter, 32/3. Calculators are wonderful things, aren't they? So going back, 32/3. All right. And our last problem, what is the volume of the solid generated by rotating about the x-axis, the region enclosed by the curve? Y equals secant x, and the lines x equals 0. Okay, x equals 0 is the y-axis, y equals 0, which is the x-axis, and x equals pi/3, which is some random line over here. That almost looks like a line. Pi/3. Okay, and secant, in case we've forgotten, starts here at 1 and goes up, well, goes up like this, and it goes up like this, but we don't care about that side because, well, we don't. Right? So we're talking about this volume here, and we're rotating it about the x-axis. So, you know, like that. And we don't need washers because it's a nice, happy, just one function thing, so nice and pretty there. All right, here we go. So we want the integral from 0 to pi/3, pi on the outside, and we're going top to bottom here, and this is secant x, so secant, and then it gets squared, so secant squared x dx. Now we could plug this into our graphing calculators, but to me it seems easier actually not to plug this into my graphing calculator, and here's why. So I'm going to have a pi here. The integral of secant squared is just tangent, right? The derivative of tangent is secant squared, so the integral of secant squared is just tangent. And then I'm going from 0 to pi/3. Okay. And then I have pi. Tangent of pi/3. Well, hopefully you guys have studied all of your trig facts, and you know that the tangent of pi/3, right? Tangent of pi/3 will be just √3. Minus tangent of 0. Tangent of 0 is 0. And so I'm just going to get √3 times pi, which is C. And the thing is, the reason I knew that this would be easier is I'm looking at my answers up here, and I'm seeing, well, pi divided by √3, pi times √3, 8 pi/3, all of these are not written as decimals. So if I plug this in on my graphing calculator, I'm going to get some kind of ugly decimal looking thing. And then I've got to try and figure out which one of those ugly decimal looking things comes out to this. And unless I'm lucky and it comes out to 3.1415926, I'm going to have to try and figure out which one it is. And God help me if it comes out to this one, right? I'm going to be there forever. So because it came out to something so nice like secant squared, where it was such an easy fix, it was actually faster, I think, to do it by hand than to try and plug it in my calculator. And especially because trying to plug secant into my calculator, now I've got to try and go FNINT, and then I got to go 1 divided by cosine x, and then square it. That's going to be a pain. And then I got to type, 0 and then pi/3. I think this is easier. So, just want to point out that sometimes not reaching for your calculator is a good thing. All right? That's it. So, best of luck. and I will see you guys tomorrow. Oh, I've lost my recorder.